Bismillahirrahmanirrahim. Assalamualaikum. Hi everyone, how are you? So today we are going to be taking solving some problems in chapter 2 in chemical process safety. So we already have finished the chapter 2, which is about toxicology. So now we're trying to solve some problems, and actually you see the real beauty of what we have taken in chapter 2 only when you look at how to solve those problems. So you will learn a lot of what we are going to be taking, honestly. So we'll start with 2.2. 2.1 is just deriving an equation, so we're not going to go through that. So we will start with 2.2. So what does problem 2.2 say? Finney reported that the data of Martin involved the toxicity of rotenone. So the rotenone is a substance that is toxic to the insect species, and the name of the insect species is the Microsophniella samborni. The rotenone was applied in a medium of 0.5% saponin containing 5% alcohol. So this was the arrangement. The insects were examined and classified 1 day after spraying. So after you spray, you are examining it after 1 day, and this is the data. And what does the data say? Is that when we have added the dose of rotenone of 10.2 milligrams per liter, and there were 50 insects there, we found that 44 out of 50 insects were affected. So that represents about 80%. 44 divided by 50 is 80%. And when we had a dose, we injected a dose of 7.7 milligrams per liter, we found out that 42 out of 39 were infected. So it says here number affected, and this is the total number of insects. And then you did another experiment. So you injected 5.1, and then you found that 24 out of 46. Okay, so the total number of insects, it's not always that you get exact number of insects. It's difficult to count them, collect them, and count them as exact. But the more important thing that they are very close to each other, so it is comparable in that sense. Okay, so that's the data that we have. So from the given data, plot the percentage of insects. We already said that we can call the percentage of insects. Yep, affected versus the natural logarithm of the dose. So this is the dose, and we just take the log, and we already have the percentage here, so we can plot that easily. Convert the data to a probit variable. How to get the probit? If we have the percentage affected, we can get the probit variable, and then we can plot the probit versus the natural logarithm of the dose, which we already have. And it will be a straight line. We're going to see that. It says that if the result is linear, determine a straight line that fits the data. Okay, so you're going to look at that. Okay, so let's start solving it. So what was the data that we had? So this is 2. Okay, so that I think so. I'm having some solution here from I was trying to solve by myself. This is 2.1, so don't worry about it. Okay, so what do we have here? We have 2.2. So in 2.2, if you look at it, I'm going to take out, this is what I have as dose. So this is what I have as dosage. And when I have done, I just took the log of the dose. So log 10.2 is 1.01, log 7.7 is 0.886, log 5.1 is 0.708. So I've taken the log, so I have not done anything different there. Number of insects with the number affected, 44 divided by 50 gives me 88%. So that's what I said. 44 out of 50 were affected, and then 42 out of 49 affected, 85.7%. 24 divided by 46, that's about 52.2%. 16 divided by 48 is exactly third, so that's 33.3%. 6 divided by 50 is 12%. And then 0 divided by 49, because none were affected, of course 0% affected. And then we start finding the probit. Okay, to find the probit, we need to go to table 2.4. And going to table 2.4, So that is table 2.4. Okay, so that is table 2.4, which is transformation from percentages to probits. So if we just look at the percentage, so if we have 88% affected, so let's go and see how we can get the probit. So that is 80. So here we can look at 80. So you already can see this. I don't know if I can access. Okay, that's fine, that's fine. Okay, so here I have 80. Okay, and here I have 8. Okay, so I hope that you already can see this. So this is 8 and this is 80, so it's 88. And when we have 88, we get 6.18. Okay, so that's the probit at 88%. Beautiful. So, and this is where you find that this is 6.18%. So let's take another example. For example, 4816, we had 33% affected. So where's 33 and what's the probit? Okay, so going to 33. So I have 30 and I have 3. And this is something like, I know it's not 33.3 exactly, but it's very close to that. So it's 4.56. So if you go and look at it, where's that? That's 4.57, right? Taking the 0.3% in addition. So this is what we have done. And after that, he asked us to plot the percentage with the log dose, and you just plot the percentage here with the log dose, and plotting the percentage with the log dose, you're going to get a figure that is to be here. So if you just want to do this like a little again, so if you talk about the percentage, so at 0 we have 0. Okay, so that's here. So at 12 we have 2.6, or we say at 2.6. Sorry, not 2.6. We're taking the log. 0.415 is 12. So 0.415 somewhere here. 12 is somewhere here. Just very roughly. At 0.58 is 33.3. So 0.58, if I say this is like 0.6 something, I'm just taking anything. So that is 33.3. 0.7, 52.2, 0.7 somewhere here, 52.2. Okay, it will be something like that here. And then we're going to continue what's left. 0.88, 85.7, so 0.88 is somewhere here, and 80 something is like that. And then we have 88, that's not much difference, with 1.01, so somewhere here. So we are going to have a figure which looks like that. Okay, so this is what we have. So that's the first part of the question, and then the question is asking us to plot the probit against the log dose. So I'm going to do this again. So what do we have here? So let's do it. So we have the log dose, which is 0.415 with 3.82. I did not include any numbers there. Oh my god. Okay, so let's put the numbers. So let's say that's 0. The maximum goes to 6 something. Okay, so 0, 1, 2, 3, 4, 5, 6. Okay, and the log dose is from 0 to 1. So we just include that from 0 to 1. So something in between will be like 0.5. And then here we have 0.25, and we have here 0.75, just for a quick figure. And let's go with the numbers. 0.415 with 3.82, so 0.415 somewhere here to 3.82, that's very close to 4. And then 0.58, 4.57, 0.58 with 4.57, something here. 0.7 with 5.06, so 0.7 with 5.06, so that is not as good as what we expected as a straight line. And then we have 0.886 with 6.87, so 0.886 with 6.07 somewhere here. Okay, and then we have like 6.18 for 1.01 somewhere here. So if you just want to draw a line like that by our eyes, and maybe that line, actually if we draw it in a better way, and I can see my axis goes up there and my 6 is here, so I would guess that this is little lower. So if my 6 is here, if my 6 is up there, so I'm going to change this a little bit because it doesn't look exactly to what I have. So 6 is here, 5 is here, just we don't want to confuse the numbers with the top. So my 5 is here, so and then I have 4, and then here's 3, okay, sorry, that's 3, and then I have like something like 2 or 1, not that exactly, I know I'm just doing some kind of roughly stuff here, like that. Okay, so this is like a straight line, and after you draw your straight line, what is the big deal of having the straight line? It reminds us with the equation. I don't know if you can remember this equation, and this equation, y is equal to k1 plus k2 ln v. It was the equation of the probit. So if you just can recall, this was the probit variable. This was the probit variable, and this is the dose. This is the dose, or they call it the effective dosage, or and let's have a look. Sometimes it's nice to just recall and remember things that we have taken. So that was yep. So that was the table. Yep. Oh, it's here. Very clear. So the causative factor, or the dose, it's called the V, and so in this case we have dose. Otherwise we are going to use the causative factor, and the probit variable is y, and so this is how we are going to calculate it. So we want that equation here, and when we have this equation, what's the beautiful thing is that if we find the slope of that straight line, we are going to find k2, and if we find the intercept of the straight line, we are going to find k1. Okay, so we can get this equation directly, and by calculating the slope and intercept, actually you can get the slope. You can get the slope here. So simply just calculating it, and we can get the intercept, where intercepts here. So this is the intercept. Okay, and that is the slope. Or you can of course get the slope, the intercept analytically, because you already have values for the probit and the dose, or the ln of the dose, and we already know the slope, for example, from the figure, so we can find that analytically as well. So k2 is equal to 4, k1 is equal to 2.2, and that is the equation that we have obtained for our problem. Great. So that was 2.2. We found the equation for y, and that was like a training of how to use the table of table 2.4, and how to find the probit, and how to find the k1 and k2, and what is the meaning of v, which is the causative factor. So all of these together was just a training to know how to use those different factors. Okay, so that's 2.2. Going now to the problem 2.3. Going to the problem 2.3, and going to 2.3, we are going to find the beauty here. Okay, a blast produces a peak overpressure 47,000 Newton per meter square. So here talking, this is Pascal, so 47,000 Pascal. We have an overpressure, peak overpressure. Okay, a blast, boom. What fraction of structures will be damaged? So what will be damaged from around that blast by exposure to this overpressure? What fraction of people will be exposed who will die as a result of lung hemorrhage. That means it's going to bleed from inside. What fraction will have eardrums ruptured? Maybe no one will die, but they will have some kind of eardrums ruptured because of the blast. What conclusions about the effects of this blast can be drawn? Beautiful. I think so. That's a very nice question. And you can see that we can find a lot of information here, very critical information and important, just by knowing the amount of the overpressure. Okay, so in problem 2.3, let me write the overpressure. So the overpressure is equal to 47,000 Newton per meter square, and we already know some kind of information, because what it is asking me, it's asking me about what structural damage we would have and how many deaths, possible deaths from lung hemorrhage. And it also asked me to know how many will be suffering from eardrum ruptures. So these are the three things that I'm trying to target here. Well, we already can recall that from table 2.4, and I think so that it's not table 2.3 is the one for the comparisons. For the probit. So here from the table 2.4, if we just go table 2.4 together and look at it, oh yeah, yes, that's table 2.4, but I don't think so we meant that. So it's not table 2.4, sorry, so it's table 2.5. Okay, so I'll correct that. So from table 2.5, what is the structural damage? What is the structural, the values of the structural damage? So we do have the values of K1 and K2. Okay, what's the idea? So what do we want to get to exactly? Because we need to know that the whole idea of how to solve that question. We want to know what? We want to know the percentage affected. Okay, the percentage affected from the structural damage, and the percentage affected for the deaths, and the percentage affected for who will have eardrum ruptures. To find the percentage affected, we need what? We need to find the probit. And to find the probit, we need the values of what? We need the values of K1 and K2, right? We need the values of K1 and K2. Why? Because what is the probit equal to? The probit is equal to K1 plus K2 ln V. Beautiful. So if I know the percentage affected, I can know the probit, and the other way around, I would know what is K1 and K2. I'm going to know what is K1 and K2. And in this case, my dosage, I don't have a dosage. What I have, the variable which is changing is pressure. So here it is pressure. Sorry for that. Pressure. So if I have the percentage, I want to get the percentage affected. How to get it? If I go and from table 2.5 find K1 and K2, and finding K1 and K2, I'm going to find Y. And then I substitute here, how to get Y, I'll substitute the pressure, and I will find Y, the probit. I'm going to find the Y probit. And by finding Y probit, then I can get how much percent will get affected. Okay, so we already now know how we're going to calculate it. So first thing we want to know is to find what? Is to find Y. But how to find Y? We need K1 and K2. And of course the value of the pressure, which we already have. So we are going to find Y, and by finding Y, I'm going to get the percentage affected. So this is what we are going to do. So just to look at it and calculate it. So what do we have here? Okay, sorry for that. I just wanted to do some kind of fancy stuff. Not used to it so far. Okay, so what do we have from structural damage? So I'm going to do this again. So from structural damage, from table 2.5, we already can see that y is equal to minus 23.8, which is K1, plus 2.92 ln P. We already have P, of course, which is the overpressure, and 2.92 is K2. So let us see, can we get these values or not? So we go back to our table. So what is the structural damage? Here's the structural damage that comes from explosion, and we can see here P naught. The values of K1 and K2 is minus 23.8 and 2.92. So minus 23.8 and 2.92, and this is minus 23.8 and 2.92. I think so, that's clear, right? So going to the next one for the deaths. Okay, of course, death from the lung hemorrhage. The Y value was equal to minus 77.1 plus 6.91 P naught, ln P naught. Okay, just want to make sure that we get these values. Again, we go to the death from lung hemorrhage, minus 77.1, 6.91. Okay, that's minus 77.1, 6.91. So yes, things are going clear for us. We are getting the exact values that we are expecting. Okay, and eardrums ruptures, we are going to get Y is equal to minus 15.6 plus 1.93 ln P naught. And if you look at that, just in a moment, eardrums, where is eardrum? Okay, eardrum ruptures, that's from explosions. It depends on P naught, which is the pressure, the causative variable. And the K1 and K2 are minus 15.6 and 1.93. Minus 15.6, 1.93. Great. So what was the overpressure that we had? The overpressure, if you just go up, it was 47,000 Newton per meter square. So the P naught was 47,000 Newton per meter square. Okay, so by substituting this P naught, I'm going to get the values of the Y, the probit. So the values of Y that I have here are going to be equal to 7.61, and the second value minus 2.76, and this means that no one is going to die. That it just means that, because it's less than 0. And eardrums, we have 5.61 is the value of the value of the probit. Okay, so depending on these values, now I want to calculate the percentage affected. Okay, the percentage affected. And where do you get this from? We get it from, if you can remember, that was table 2.4. That was table 2.4. And let's look at it. 7.61. So we go to 7.61. We go to the table at the top. And as I said, that we can use either the table or the figure. But the table is easier. So 7.61. 7.61 is between 7 and 8. Something between 7 and 8 is, it's not easy actually to calculate it from here. So 7.61, sorry, it's not 7 and 8, this is for the percentage. So 7.61 is between 7.58, okay, and it's between 7.65. So 7.58 and 7.61 is like something in between those two. Okay, something in between those two. So you're talking about, oh my god, 99%. You're talking about a very high number here, which is 99%. Okay, so we will say that will be like 99.7.61, 99.6. Yeah, like something like about 99.6, right? Okay, you see here 99 and 6 was something like that. So here we say that's about 99.6%. Let's go to the second one, minus 2.76, definitely it will be, that means 0%. 5.61, 5.61, so where's, okay, that's an exact number, good. So that's 73, right? So that is 73. Am I correct? What did I say, 70? Again, 5.61. Okay, so that is, yes, 73. That is 73%. So we need to substitute that, and we found that 73%. And let me just make sure from the figure, if we get something similar, 5.61, actually it was not 5.61, sorry, it was 5.16. And that is why I was confused, because I solved it before I solved it to you and it was different. So depending that it was 5.16, now the answer is different. So 5.16, now it will be something like in between these two, 5.16, so it will be something like 50, it will be 5.16, 5.1, 5.1, 5.1, 5.15, which is close to 5.16, which is 56. Okay, great. So here it will be 56%. Beautiful. So these are the numbers that we have obtained, and we can know that even though you can see that the blast that is so serious, in the sense that not enough, that it is not enough, to cause any death, right? There are no deaths at all. But imagine how many, what's about the structure damage? 99.6% of structure, right? Of structure will be damaged. And it's not only that. Imagine how many people are going to get an eardrum rupture. We have 56% of eardrum rupture is expected. Oh my God. So you can see, like, just by knowing the overall pressure, we can decide, we can know, we can talk about like what will happen. Imagine half of the people, if you have 100 people, half of the people, they're going to have a problem with the eardrum. And this is why it is important, and this is the beauty of what you are trying to see here, is that we can know how many people are going to get affected, how the structure is going to be getting affected, just by knowing the information. And all what we have used was the values that we have already trained ourselves with, which was the probit, and the values of K1 and K2, the values of K1 and K2 that we just have seen here. I just want to show you that. So they call it the probit parameters, and it depends on the causative variable, which is V. As you remember, Y is equal to K1 plus K2 ln V. V here is the causative variable. So in the case of explosion, it is the pressure. So we just took the pressure. But in the case of toxic release, which we'll take in another example, we need to use the V as these variables, okay, as this equation, and so on. So that was the problem 2, 3. I hope that you liked it. There was a beauty of, there's something that we got to understand here, and we feel that we did a good job telling our manager that this was what could happen, so we need to do something about it and put care into it. Okay, great. So that was 2, 3. Okay, so let's now go to 2, 4. 2, 4 is a bit long one. It's not difficult actually, but it just has many different ideas into it. So if we go to 2, 4, so the peak over pressure the peak overpressure expected as a result of the explosion of a tank in a plant facility is approximated by the equation log P is equal to 42 minus 1.8 log R. So here talking about the peak overpressure, okay, the peak overpressure as a result of the explosion is approximated by that. Okay, so the peak overpressure will be higher if the radius is very small. So this is the relationship that we have. So if you're far away from that explosion, it will be less effective. So that is the idea. So where P is the overpressure and R is the distance from the blast in feet. The plant employs 500 people. So there are 500 people. So depending on what radius do I have, these 500 people are working around that place, around that column. And of course we are going to assume they are distributed evenly. Not all of them are sitting in one place. So 5 people who work in an area from 10 feet, which is possible 10 feet away from that column, because the column is already surrounded as a protection area, not to enter. So 10 feet to about 500 feet, which is like, let me say, the limits of the plant. That was the limit of the plant where the employees can walk in. Okay, for 10 to 500 feet. Estimate the number of fatalities, oh my god. So number of deaths, number of fatalities expected as a result of lung hemorrhage, and the number of eardrums ruptured again as a result of this blast. Be sure to state any additional assumptions. Okay, so now we want to calculate the number of fatalities expected. So what we are going to say here, just to get the idea, if we have an idea about it's just we are going to substitute different radiuses, and by having different radiuses, if it was 10 feet, if it was 20 feet, if it was 30 feet, if it was 40 feet, and so on. So if we have different radiuses here, we are going to have different overpressure, and by having different overpressure expected at that radius, this P it is the P naught that we use in our calculation. If you remember the P naught, so this P is that P naught, and now we can calculate. You can see here, right? We can calculate the Y, the probit, which is a function of K1 plus K2 ln V, which is ln P. So we can calculate Y, and from the Y we can go to table 2.4 to calculate the percentage affected. Okay, so I think so that is very clear of how we are going to solve this problem. However, we are not sure how these people are distributed, so we can't calculate the percentage affected. It just gives me the percentage. So I don't know how many people are within that radius. So I need to know how many people are within that radius. Okay, so that I can calculate the percentage of those people are sitting in that radius. And it's very simple to calculate how many people are sitting in that radius. I just take the total area of this place and divided it by 500 to say how many people are sitting evenly in that area from 10 to 500. And then when I find the number of people that are sitting in that radius, I can say I can take the percentage of that. So just to write the equation, so this is the column, okay, and it has something surrounded by it, so that is about 10 feet. And if I go to something like bigger here, so that is like 500 feet. And if I just draw some kind of different radiuses, so this is a radius, this is another radius, and this is a radius, and so on, right? So this is what is around and how the people are working around here. So to know how many people are sitting within a certain radius, so how many people are sitting within a certain radius, so they are sitting here, for example, in that radius. Okay, we want to calculate that. And how to calculate that? To calculate the percentage of those people who are going to get affected at that radius. So the explosion equation, let me write that. So it's log P is equal to 4.2 minus 1.8 log R. Okay, so that is the equation. And to calculate, we already said the idea of changing the radiuses, and calculating how many people and so on. Before I do that, I just want to know how many people, how they are evenly distributed. I would say evenly distributed, and that is a good assumption that I'm going to take. So the assumption that I have here, so the assumption that I'm going to add here is that the people are evenly distributed. Okay, so they are evenly distributed. Okay, so that is my assumption, and based on that assumption, what is my area? My area is pi r square, and that pi r square starts from 10 because no one can be inside there till 500. So in this case, it will be like pi r now it will be like 500 square minus 10 square. So I'm taking the area minus that smaller area, which is the one inside, is equal to 7.85 into 10 to the power 5 feet square. Okay, so what is now the number of people? The number of people who are going to be in that place. So the population density is called the population density. So we have 500 people per that area, right? 500 people per that area, per that area that I have here. So I have how many people per feet square? So we will have 6.37 into 10 to the power minus 4 people per feet square. So that is the number of people that I'm expecting. But I know you're looking at a small number because it says per feet square, and just don't think of it like that, but think of it that if you increase the feet square, you will get an exact number of people, because there's no 0.00 number of people. Okay, so that is what I have now so far. So now I want to look at this different radiuses or shells or whatever you want to call them, and to calculate the percentages as we have just mentioned earlier. So let's start. So the death that you could have due to lung, okay, due to lung hemorrhage. Okay, we already had seen that in our previous problem. It was minus 77.1 plus 6.91 ln P, right? And we already know P. Oh, do we really know P? Yes, of course we know P. We can calculate P. We can calculate P from the radius, right? And we're going to come to that in a moment. So let's go to the eardrum, because they're also asking about the eardrum rupture. So the eardrum rupture, it was y is equal to minus 15.6 plus 1.93 ln P. So do we know P so that we calculate Y, and from Y we know how much percentage is affected? Okay, so that's the idea. Yes, we know P. How do you know P? We can know P from already the radius that we have, the overpressure at a certain radius. So let's start with it like that. If we don't want to have any death at all, okay, if the probability is equal to 0, if the probability is 0, then Y is equal to 0. So when you calculate the overpressure, so that would be 0 is equal to minus 77.1 plus 6.91 ln P naught. What I'm going to have here, you are going to find that the P naught is equal to 10.17 psia. So that is the overpressure that I would have. Okay, at probability is equal to 0. And very similarly, just for the eardrum, so I just calculated that for the first part, and for the second one, where we have for the eardrum rupture, the P naught, that P naught is going to be equal to the exponential of 15.6 divided by 1.93, and that will be something like 3.24 into 10 to the power 3 newtons per meter square is equal to 0.47. Okay, sorry for that, which is equal to 0.417 psia. Okay, there was I skipped one step here because it was already in Newton per meter square, and then you need to find it in psia. So I'll just write that so that you don't get confused. So that was 7.01 into 10 to the power 4 Newton per meter square, which was equal to 10.17 psia. Okay, so that was it. So now, depending on what we have as P naught, this will occur, this will occur at the following distances. So that overpressure that we have, will occur at the following distances. So the depths that we have, if we just calculated, log R is equal to 4.2 minus log P divided by 1.8, and we are going to get an answer. Okay, so what will be R? R is equal to 59.4 feet. So now we know the radius, and for the eardrum, I forgot to say here that this depth is only from the lungs hemorrhage, right? It's not any depth. So, and then we have the eardrum rupture. Very similarly, log R is equal to 4.2 minus log 0.47. That's the 0.417 that we already have obtained. 0.417. It was 0.47 actually. Okay, so I'm just going to correct that. That was 0.47. So here's 0.47. 0.47 divided by 1.8, and that is equal to, the radius is going to be equal to 328 feet. 328 feet. So we can see that the depth calculation can be performed using a single shell, 59.4 feet in radius, and with the number of at the radius of 59.4 feet, I can know how many people are sitting there. Okay, so how many people are sitting there? So let's calculate it. So looking at it, I calculate the area at 59.4 feet, that will be equal to 10,771 feet square. And by that I can calculate how many people are sitting there, because I already calculated the feet, the area at that place till that place. And if you multiply this, okay, if you want to know how many people in that shell, in that place area that we are targeting, is going to be equal to 10,771 multiplied by the number that we had already obtained, that how many people are per feet square, right? So we have this much of people, okay, this much of people per feet square, and this will be equal to 6.86 people. So let's say that we take the smaller number, that we say 6, right? We just say 6 people. Okay, about 6 people. So talking now about 6 people, now within that radius, as we have said, our example of the column, okay, so at that radius, which is 59.4, so there are people at this shell, right? But there are people here as well, right? There's people also in the middle. So if we take an average radius in between, and actually I'm just saying many different kinds of solution. I mean, we could have done it in a different way, as I have mentioned in the beginning. So depending on the number that I have here, which is 6, I can calculate, let me say it in another way. So number of people affected are 6. So we know that now, right? And we know, and if we want to calculate the percentage of people who are going to die here, we need to calculate what? We need to calculate the probit. And from the probit, we can calculate the percentage. Well, if we just consider somewhere in between here, which is the average radius, plus 59.4, because there are many people sitting here, right? That's what I'm trying to say here. 34.7 feet. And by that, I'm just talking about, so the pressure here definitely will be higher. So there is a very high pressure here. It's less there, and is going to have some kind of an effect. Just for the sake of calculation, so if my average pressure, overpressure I would say, if my average overpressure is equal to 28.1 psia, and I don't know if you can recall what was the overall pressure that we had here. It was like 10.17, and we had yes, it was 10.17. And something in between, yes, it was the 10.17 that was from the death, 10.17 for the death. And actually, what was the area? Let me see that. Sorry. So the question said that, yeah, that was the overpressure. So we calculate the overpressure depending on the average radius. So if we calculate the average radius here, we can know how much pressure that we have, and when we calculate that pressure, it will be 28.1 psia. And when you calculate that, we can calculate the probit variable, which is y is equal to minus 77.1. You already now know those numbers. Ln of that pressure, 1.94 into 10 to the power 5. So that was the pressure at a certain radius. I know that we have went and overall calculating how many people we have here and there. We could have done that easier by calculating the number of people, and then we just take the overpressure that we are expecting at that place, right? Okay, because we just get that from the equation. Okay, so that is equal to 7.033, and from 7.033, if you go to table, again from table 2.3, you're going to find out that 97% means what? Yani if you take 97% multiplied by the 6 point, what was that? The number 6.86. You're getting something like 6. Okay, so you're talking about 6 people definitely are going to die. Okay, wow, 6 people definitely are going to die because of that. And similarly, you can do that for the eardrum. Actually, I would prefer the other method in which we can do a better kind of a calculation, and where what we are going to do, and that was the thing that I was trying to target at the beginning. So if we have the shell numbers, we divided the area from 10 to 500 feet into different radiuses. So shell number 1, shell number 2, shell number 3, and I know I don't know if you know what the meaning of shell here that I mean, but I mean different radiuses, right? So talking about a certain radius from 10 feet. So talking about something and a radius of for example at 20 feet, and then at say 50, and then at 100, and then at so if you just want to make it even, that would be even better. So we'll say like the radiuses of 50, 100, 150, 200, 250. So we can put radiuses, and based on the radius, of course, we can calculate the area, and based on the area we can calculate the population density, and we know the number of people sitting in that radius area, right? Number of people sitting in that radius area. But it's not only the number of people sitting in that radius, there are still people within closer, and this is why we have taken the average of people. So and then you calculate like the number of people, or not only on that radius, so the number of people in total, and that we took that as an average value as what we have done. And based on that, of course, of calculating the whole idea of, we want to calculate how many people are sitting there, right? How many people are sitting there. And then we know how many people are sitting there, and we take a radius which is something in between. Okay, so we are going to calculate the pressure, from the average radius. So this is a total average based on the average radius, and based on the average radius I'm going to calculate the number of people. Well, I already calculated number of people. I'm going to calculate the P naught, and from the P naught I want to calculate now Y, which is K1 plus K2 ln P. Okay, just a moment. So ln P, I already have ln P naught. So I'm going to calculate the pressure, and based on the pressure I can continue and calculate how many people are going to get affected. So I'm going to get the value of Y, and after I get the value of Y, I'm going to get the percentage of people, and then I'm going to know how many number of people are going to be getting affected. So you see the big table that I'm trying to build here. So that is a big table that I'm trying to build here, and build my case. And my case that I'm trying to build here, finding the whole radiuses. Okay, 300, 350. So I'm trying to find within all radiuses what is going to happen. What is going to happen at all radiuses, and I can calculate the number of fatalities. The number of fatalities that I do have. So I think so. Like, hopefully that you liked what we are doing here. We liked what we are doing here, and this is what we are trying to calculate. Well, within your there's another way. Actually, there's something else came to my mind. Rather than calculating also in this way, we also can mention the shell numbers. Don't worry about the shell numbers. It's all about radius. Okay, right? So it's all about radius. So we want to see how much from 10 foot till 68.7 foot, and then we take the average radius, which is 39.3 radius, and based on that average radius I'm going to calculate the pressure. Okay, so for example the pressure was 21.4, and based on that pressure, this is the pressure and PSIA, and then I can calculate the pressure in Newton per meter square, of course, because that we need to have it in newtons per meter square to calculate our probit. Okay, and then we are going to calculate our probit, and from calculating our probit we can know what is the percentage, and knowing the percentage we can calculate the number of people. We already have the population density, so we can calculate the number of people. So we can do this, like we can calculate from 10 to 68.7 radius how many people are going to be affected. Then you're talking about, we are basing our calculation on what? On 39.3, which is the average. Okay, which is the average, someone in between all of these people who are getting affected, and the people who are sitting from this radius to that radius, which is an average of 82.6, and if we calculate it, it will be 5.62 PSIA, and the pressure based on the equation given by the problem, okay, the P with the log R, we can calculate 3.87. We can calculate 5.62 and then convert it to 3.87 into 10 to the power 4. And then you can calculate the probe, which is 4.79, and the percentage getting affected, which is 42%. Okay, 42%. And then we can calculate, okay, and then we can calculate the number of people getting affected, which was 3.9. Okay, so you just multiply now 42% with the number of people getting affected within that area, depending on the population density. So I'm going to put the numbers here for you to do more kind of calculation, just to feel more comfortable about it. So I'm just trying to have this, yes, zoomed in in a sense that I still have everything in one page, so that I can write freely. Okay, and so on. You can continue. I'll try to do this quicker. So from 96.6 till 118.2. So that is another radius. And this is and why do we have these numbers? I forgot to tell you. Why do we have these numbers? I'm just trying to distribute it into equal shells. Okay, so it depends on how many radius shells you want. You want to divide it into 5 shells, into 10 shells, into 20 shells, and each one is going to give you a different amount of numbers in each shell, and how many people are going to be affected in each shell, and so on. Okay, so let's continue. So that will be 350 psi, and that will be 2.41 into 10 to the power 4 Newton per meter square. And here we were going to have 3.87 the probate, and where we will have 13%, and 1.2 people will die, and so on. So hopefully I got this right. Okay, 96.6, 118.2, 117, 350. Yes, I think so. I'm fine with that. Okay, and you can continue with that. Okay, so from 118.2 to 136.3, that was the average radius, in which, based on that radius, I'm going to calculate from the equation given the problem 2.58, and then convert it to P naught. And from the P naught, I can get from that table, I can get the number for the probate, and the number for probate is 3.29, where we can calculate the percentage from table 2.3. And of course, if we multiply by total number of people in that area, I'm going to get 0.4. And then I'm going to continue with that to have from the radius 136.3 till 152.3. And I already can see that I'll not go further than that from these radiuses, because I'm already getting something very close to 0%. So there's no meaning for me to even count more and more. So I'm going to be stopping here. So just 1.7%, and the number of people getting affected is only 0.2. So I don't think so. I want to calculate more. So if I now want to calculate the total number of people who are dying, about 14.8, which is something like about 15 people, right? So of course we can make better estimates if we take even smaller and smaller shells. So how many shells did we have? So we have divided that into 5 shells. So we divided this into 5 shells. And this is what we had here. We are talking about fixed number of people per shell, and we are talking about equal radiuses increments. So this is what you are trying to do here. And to divide it into equal shells, just to get the idea, we already know how much feet per feet square, right? We already calculated how much feet square do we have, and the number of feet per feet square, that was at the top here. Yeah, it was 59.4 feet square minus 10 square, which was equal to 10,721. So that was the amount of feet square that we had. Okay, so if you divide that into 5 shells, you will get the details of what we have tried to mention here. There's one point that I would like to mention here, and that is if we have different areas, area we are talking about, in the sense that if you're talking about higher areas, if you're talking about higher areas, yes, you will not have anyone affected. If you're talking about the smaller, closer areas, there are more people maybe getting affected, in which in this assumption we are considering that there is some kind of there are some errors within this problem in which that we did not consider, but we still can calculate the total to be 15. Okay, the only thing that I think the question that comes to your mind is that this is 99.1% are affected from how many people? Okay, from how many people who are sitting in that small density area? Okay, in that small density area, and this means that from the population density, that means the 1 per feet square that we have, we can calculate how many people are sitting within this big density area. You already can calculate the total area. What I'm trying to say here, that you calculate the total area that we have, and based on the total area, I'm going to calculate the total number of people. Okay, and the total number of people, and if you have only 500 people, right? If you have 500 people, already we know that we have 500 people. If you divide that into 5 shells, you're going to have 100 people per shell. Okay, so you're going to have 100 people per shell. But are all of these people, like, they are distributed within these 5 shells? Is it a good assumption or not? Or there are more people out of those shells? And so if you divide that into like more accurate, you're going to take half of this number, which is about 50. Because there are going to be people who are even farther than that. I don't mean farther, but this is assuming that they are equally distributed, right? Equally distributed, depending on the total area that I have. And by that, I can calculate how many people are sitting per shell, right? How many people are sitting per shell. So depending on the number, so if it was 50 people, per shell, then we are going to multiply 99.1% into 50. Okay, so that is the point that I'm trying to target here. So it all depends on the number of people sitting in that shell, that whole shell that we have. And that is the number of people depending on what? Depending on the total area that we had. We already calculated 6.8 for the example that we had at the top. But I'm just trying to say that we may have a different number of people based on which we can calculate different numbers. As I told you, this was like a long problem. I knew that it would have taken much of time, and that was 2.3. I know 2.3 was going to be a bit challenging. It has a lot of details, but it was a good problem that we wanted to cover and test ourselves